Hello, everyone, and welcome to week 13. This week, we're going to discuss chapter 15, which is on glaciers and glaciation. This is one of my favorite topics, and hopefully, it will be interesting to you as well. And before I get started, it's important to note some of you may be thinking, why do we even care about glaciers if we live in Nampa or Boise or Caldwell or the surrounding areas? And that's a great question. So part of the material I'm going to cover in this chapter is not only talking about glaciers themselves and the water that they hold and the sort of erosional forces that they cause, but also how past glaciation events have changed the Earth's surface in really dramatic ways that still impact us here in the Treasure Valley, as well as many other areas where glaciers don't currently exist. So that's important to keep in mind throughout this lecture. So first of all, before we talk about glaciers in depth, it's important to understand exactly what a glacier is. So a glacier is a thick mass of ice that forms over hundreds or thousands of years by the accumulation, compaction, and recrystallization of snow. So some of you may wonder why a glacier looks like ice versus, a snowpack. You can still see some of the characteristics of the original snowfall to some extent, and that is because of the compaction and recrystallization. You can think of the formation of glaciers similar to if you're thinking about sediment and you're depositing sand in a basin for hundreds or thousands of years, and then that sand becomes compacted and then cemented together to form sandstone. It's sort of analogous to what happens with snow compacting and recrystallizing into glaciers. So, kind of as previously mentioned, even on the opening slide, glaciers are part of two basic um, cycles in the Earth system. First, obviously, the hydrologic cycle is a really important is a really important cycle that glaciers are involved in. So water can be trapped in a glacier for many years. So one really cool example is the Antarctic ice cores have been found to hold water for up to 800,000 years. So you can core ice that's 800,000 years old that has evidence of what the environment on Earth in that location was like 800,000 years ago. Pretty cool. And then glaciers are also a major part of the rock cycle because glaciers erode and deposit um, anything from massive rocks to sediment. And, not only erode and deposit uh, these things, but also different aspects of glaciers can sort sediment and rocks in different ways. Which is very important for us because one of the most expensive things about procuring rocks or sediment like a sand or a clay as material resources for humans, one of the most expensive parts of that is actually sorting the material. But if it's already been sorted for you, then that's a massive advantage for us. And it also has interesting implications for the uh, geologic alterations that glaciers cause and how that impacts the natural environment today, both in places that are glaciated and places that were glaciated in the past. Okay, so we talked about what a glacier is and how it impacts both the rock cycle and the hydrologic cycle. So let's expound upon that and talk about a couple of different types of glaciers and how they impact the rock cycle and hydrologic cycle differently. So first, you have valley, or otherwise known as alpine glaciers, and these are glaciers that exist in valleys of mountainous areas. Um, One really good example of this that's pretty near us here in the Treasure Valley is Glacier National Park. And if you've never seen it, I highly recommend that you search for some photos of Glacier National Park or take a look at it. on Google Maps and Earth View. It's one of the most beautiful places I've ever seen. And not only has a lot of alpine glaciers, but also has a lot of geologic evidence of alpine glaciers that has existed there in the past. One of the other most common types of glaciers are ice sheets, and ice sheets exist on a much larger scale than valley glaciers. So instead of conforming to a valley, an ice sheet is so massive that it moves over top of mountain ranges and plateaus and valleys, all of it. And some examples of this on modern day Earth are in Greenland and Antarctica. And those are really the examples of ice sheets that we have now. But it's important to also recognize that only 18,000 years ago, ice sheets extended down into northern North America and even impacted some areas in Idaho as a result of the Cordilleran ice sheet extending into eastern and northeastern Idaho. So this is an example of what a valley glacier or alpine glacier might look like. This is the Hubbard Glacier in Alaska, and you can see that it's sort of coming down in between a couple of mountain ranges. And then you can also see this sort of black line or dark colored line that dissects the glacier. And I want you to think about why that might exist there like that. Why is there this dark line in the ice? And then we'll get to that later in the lecture and cover what exactly that is. And since I just showed you an example of an alpine or valley glacier and what that looks like, to see an ice sheet, you really have to, you can't just take a photograph of an ice sheet and be able to see it very well, unless you're taking that photograph from space. So these are a couple examples of major ice sheets here. So you have Greenland, whose ice sheet occupies about 1.7 million square kilometers or 663,000 square miles. So about 80% of the entire island of Greenland is occupied by an ice sheet. And then in Antarctica, you have about 5.5 million square miles covered with an ice sheet. And the ice shelves, which aren't on land but are ice that exists out on the ocean that's attached to the continent, occupy another 1.4 million square kilometers or 546,000 square miles. So the ice sheets off of Antarctica occupy about as much space as the entire the ice shells off of Antarctica occupy about as much space as the entire ice sheet of Greenland. It's a crazy amount of ice. And it's important to keep in note as we go through this lecture as well that, during the last ice age, we had ice sheets at a lot of locations in the world that were pretty far away from the North Pole and South Pole, actually. So there was plenty of ice sheet activity in Idaho, for example, during the last ice age, which ended about 10 to 12,000 years ago. So we talked about the ice sheets of today. However, let's talk about the ice sheets that existed during the last ice age a little bit more. So about 18,000 years ago, which, in the span of geologic time actually isn't that long ago, ice sheets still covered very large portions of North America, Europe, and Siberia. And over the last 2.6 million years, ice sheets have advanced and retreated several times. And this figure that I'm showing on this slide shows the extent of the ice sheets about 18,000 years ago over North America. And so there are portions of eastern and northeastern Idaho that were covered by the Cordilleran ice sheet, small portions of eastern and northeastern Idaho, and then there was a lot more alpine glaciation in the mountains during the last ice age as well. So um, if you hike through the mountains for, let's take the Sawtooths for example, you can see a lot of evidence of this glaciation that existed only 18,000 years ago. So when I talked about present day Antarctica and how the whole continent is covered by an ice sheet and also there are ice shelves that extend from the continent out into the ocean, let's talk a little bit about what those ice shelves actually are and how they impact our surface. So ice shelves in Antarctica form in areas where glacial ice flows out into the sea. So this ice doesn't actually form in the sea or in the ocean itself. It forms on land and then it flows out to the sea. And in shallow water, for example, a lot of times near the coast of the continent of Antarctica, the ice touches the bottom, the ocean bottom, and is, sort of quote unquote grounded or attached to the ocean floor. And then in deeper water, usually further out from the continent of Antarctica or other continents that have ice shelves, the ice shelf just floats on the water. Usually ice shelves are thickest on the landward side and thinnest on the seaward side, which sort of makes sense when you think about the ice flowing away from the land out into the sea, and then the sea perhaps causing additional melt of that ice. Additional melt relative to how much of it would melt if it was on land. And some ice shelves are unstable and are starting to break apart. They're always breaking apart and reforming throughout the history of glaciation and ice sheets and ice shelves. But recently, due to climate change in Antarctica, there's been additional breakup of ice shelves and additional dissipation of the ice shelves as they've melted into the ocean. So this figure shows some good examples of the features of ice shelves that I just described. So you can see here how in the shallow water the ice shelf is grounded or touching the ocean floor, and then in the deeper water the ice shelf floats on top of the water. The reason why ice floats on water is because to form when water forms into a solid, it crystallizes, and that crystalline form is less dense than water, on average about 9% less dense than liquid water. And that's why it floats on the surface rather than sinks to the bottom of liquid water. And then ice melts from the ice shelves, and material is transported by the glacier and released and falls to the ocean floor. So, sediment and rocks that were transported by the glacier that are pushed out onto the ocean by the ice shelf, as that ice shelf melts, that sediment and those rocks fall to the ocean floor. And these rocks are called drop stones. And then you can see examples of a couple of icebergs as well. And major icebergs are often the result of ice shelves breaking apart out in the ocean. So this photograph here is a really great example of a drop stone. So you have a bunch of sediment being deposited. This location was probably once an ocean basin that ice sheets were flowing out into, and so there were ice shelves there. And you can see all the sediment that fell from the glacier, but then the glacier also transported this massive rock, and that rock also fell to the ocean floor, and then it was incorporated in the sediment that built up over years and then ultimately formed a sedimentary rock. And this is a pretty classic example of what a drop stone might look like. Um, there aren't very many geologic forces that are capable of moving a rock that large, and even when they are, it's unlike it's unlikely that anything but a glacier would move a rock that large and just drop one rock that's that large at a point in time. Because really, the only other thing that can move things like this is a landslide, and you would see a bunch of large rocks around, but you only see the one. So if you ever see something like that, probably a drop stone. So some other types of glaciers include ice caps, which are different than ice sheets, and ice caps completely cover the surrounding terrain, but are much smaller than ice sheets. They're sort of in between alpine glaciers and ice sheets in their size. And you can see that Iceland is a really good example of ice caps here. So ice caps cover some uplands and plateaus, which is different than the valley, or otherwise known as alpine glaciers, that only flow through valleys. Um, so I'm going to talk about a couple other types of glaciers before I move on to describe some of the ways in which glaciers impact the rock cycle and hydrologic cycle. Um, so ice caps, like you might see in Iceland, and ice sheets, like you might see in Greenland or Antarctica, feed what are known as outlet glaciers, which are kind of, you can think of them as sort of tongues of ice, or a tongue-shaped piece of ice that extends outward um, from the larger masses, or from the ice caps and ice sheets. And they're sort of analogous to what an alpine or valley glacier might look like, but really it's the ice cap or ice sheet that's feeding it, rather than an alpine or valley glacier, which kind of exists as a self-contained feature. Another popular type of glacier is a Piedmont glacier, and these form when one or more alpine glaciers emerge from valleys and spread out in a broad lobe um, within another valley that's within a lower elevation valley or larger valley. And so some good examples of Piedmont glaciers can be found at Axel Heiberg Island, which is in the Canadian Arctic, and that is what this photograph here is from. So where do glaciers form, and why exactly do they form there? Well, in the simplest terms, glaciers form in areas where more snow falls in winter than melts during the summer, because you need an accumulation of snow for snow to become deep enough to become compacted and then to crystallize into ice, which is what a glacier is. So it's really a mass balance situation of the amount of snow coming in versus the amount of snow melt going out. Um, so one term that refers to this mass balance that is interesting to note is the snow line. And snow that exists above or at a higher elevation than the snow line does not melt in the summer. And because it does not melt in the summer, anything above the snow line is a prime location to ultimately form a glacier. However, it's also important to note that the elevation of the snow line can change drastically as a result of climate change. Um, so how do snowflakes actually transform into glacial ice? How does that compaction really take place, and how does the crystallization actually take place to form that glacial ice? Well, basically, you have air infiltrating into new snowfall, and that air um, causes some partial melt of the snowflakes, and the snowflakes then become smaller, thicker, and more spherical, and that forms something which is sort of an intermediary step between just snow and glacial ice, and it's called firn, F-I-R-N. Okay, and once the original snowfall has recrystallized into a much denser mass of small grains called firn, then if that firn um, plus any other ice or snow ultimately comes to exceed a depth of 50 meters, then the firn fuses into a solid mass of interlocking ice crystals, or glacial ice. And this type of accumulation of snow and recrystallization into glacial ice can ultimately take tens to hundreds of years to achieve that much snow buildup and the transformation of firn into glacial ice. Alright, so you've formed glacial ice. Maybe it's appended onto an ice sheet or an ice cap or an alpine glacier. Now, how does that ice move? Because previously we talked about, for example, on ice sheets, you have the ice flowing out into the ocean and forming ice shelves. Well, how does ice move? It's a solid, after all. So glacial ice moves as flow, and plastic flow involves movement within the ice. So even though it's solid, there still is movement within the ice. And under pressure, ice behaves as sort of a plasticky material. And for those of us who have interacted with plastic, which is probably just about everybody, you can note that most plastic can be bent. Another type of flow or movement of a glacier is called basal slip, and this is when the glacier is moving along the ground surface, the entire ice mass slides along the ground, and that is known as basal slip. And that often occurs because meltwater from the glacier acts as a lubricant that causes the overlying glacier to slide along the surface. So not only do you have sort of a plastic flow within glaciers themselves, but you also have basal slip that moves the entire glacier from bottom to top as well. So those are two different ways that glaciers move. All right, so this figure shows a really great example of the different types of glacial movement occurring at the same time. So ice in the zone of fracture, which is usually the top layer of the glacial ice, is sort of carried along with all of the movement that's occurring below, piggyback style. And we'll get into why it fractures like this near the surface in a moment. And then below a depth of about 50 meters or 160 feet, ice behaves plastically or has that plastic type of movement that we just talked about, where it deforms without breaking and sort of gradually flows. And it flows this way here instead of fracturing due to all of the pressure of the overlying ice. And then finally, at the bottom of a glacier, you have this basal slip occurring. So at the bottom, you have the basal slip. In the middle of the glacier, you have this plastic-like internal flow. And then at the top, you have the total movement, which is the basal slip plus the internal flow, contributing to the movement of the glacier near the surface. So let's look at the zone of fracture in a little bit greater detail, because the zone of fracture, after all, is really what we see when we look at a glacier, because we're looking at the glacier's surface. So some of these fractures in the ice are known as crevasses, and they're present in the zone of fracture, but sealed off by plastic flow at depth. So, if one were to fall into a crevasse, you don't come out at the bottom of the glacier, you actually get trapped deep within the glacier, in the zone of plastic flow. Pretty scary. So if you're ever hiking around a glacier, please be careful. Now, how fast do glaciers actually move? Um, this is important to understand um, to better understand how glaciers impact the surface of the Earth, after all. So similar to surface water, glacial ice, the solid form of water, moves at variable rates. The flow is fastest in the center of the glacier, where you have that plastic flow that we've been talking about. And it's slower near the ground surface and near the top of the glacier. And glacial velocity ranges from extremely slow to several meters per day overall, as far as the total velocity of a glacier. So some glaciers exhibit extremely rapid movements called surges, and these movements can be up to 100 times the normal rate. These surges are often caused by increases in water pressure beneath the ice that cause a massive basal slip, for example. So maybe a bunch of water that has melted from the glacier is getting trapped beneath the glacier, and that builds up immense pressure that causes a very large basal slip. So let's look at a real world example of how fast ice actually moves and how this rate of movement actually can vary dramatically even within one particular ice sheet, like the Antarctic ice sheet. So the slowest movement in the Antarctic ice sheet is along divides. Divides being the high elevation points within Antarctica. And then as you move away from those divides, the rate of movement of the ice goes from less than 1.5 meters a year quickly to over 10 meters per year, or the green shaded areas within Antarctica here. And then finally, as you get towards the margins of the continent, as you get towards the ice shelves, you can see that the rate of movement of the ice can be, up to 1,000 meters a year or more. So in those areas, the ice is moving very quickly. And as you might imagine, some of the increased rate of movement of the ice is because towards the margins of the Antarctic continent, it's warmer, there's more exposure to seawater, etc., that can cause much greater amounts of basal slip and can cause the plastic flow within the glacier to be more plasticky, as warmer material can typically flow more rapidly than a colder material. So moving on from sort of the movement of the ice, let's talk more about the budget of a glacier, or the mass balance equation that causes a glacier to grow or shrink over time. And this is particularly important these days, as a lot of glaciers all over the world are under threat, and it's because the results of this mass balance equation have been altered by changes to climate, be they changes to temperature or changes to precipitation, magnitude, or timing. So there are a few different glacial zones to consider when thinking about the mass balance of a glacier. So you have the zone of accumulation, or inflow, and this is the area where a glacier forms, or where it grows. And this area is located above the snow line, because again, the snow line is the elevation above which the snow that accumulates during the winter doesn't melt during the spring or the summer. And then below the zone of accumulation, below it in elevation, you have the zone of wastage. It's kind of a cool name, right? Or outflow. And this is the area where there is a net loss of glacial ice. And this is due to melting of the ice, and also a process known as calving, where large pieces of ice break off of the glacier, forming icebergs where the glacier has reached the sea. And this also happens at ice shelves, obviously, where you have these calving events. All right, so this slide shows the glacial zones that I just described on the previous slide in a figure format. And so you can see the zone of accumulation is the highest elevation area, where more snow falls each winter than melts each summer. And this zone is above the snow line, which is depicted here, which again is the elevation at which it's the lowest elevation at which more snow falls each winter than melts each summer. And then below the zone of accumulation, you can see the zone of wastage, which is where all the snow from the previous winter melts along with some of the glacial ice. And this is below the snow line as well. And then you can see some of the crevasses on the surface of the glacier, which a lot of these fractures in the ice are caused by the different rates of movement of different portions of the ice. So as I mentioned previously, the center of the ice is moving faster than the top or the bottom of the ice, and that creates these fractures. And then, if you remember from a previous slide, I showed you an Alaskan glacier, and there was this dark line that sort of dissected the glacier in the middle of it. And in this figure, you can see a couple examples of that. You can see these brown lines, and you can see that they actually form when one glacier flows into another glacier, because both glaciers are transporting sediment on the edges of their flow, and then that leaves traces of the fact that the glacier in the bigger valley is composed of multiple glaciers from smaller valleys, and that is called a medial moraine. And then at the end of the glacier, you can see what is the terminal moraine, which is where sediment is deposited at the end of the glacier from erosion as the glacier moves downslope. And then draining out of the glacier, you can see graded streams. So if you remember from the surface water lecture a couple weeks ago, glaciers are one of the most common sources of graded streams. So now I'm going to show you some really cool videos of a couple of calving events. So if you remember, calving is when a glacier, a portion of a glacier breaks off into the sea. So I want you to be able to see this firsthand. And one of these videos is going to be the largest calving event ever caught on film to date, which is pretty amazing.
Here comes the water. Uh-oh. Look at that. Ouch. Uh-oh, uh-oh. That will be all right. Ouch.
on the phone with Jim on one of our regular check-ins. Like, Jim, nothing's happening.
Jim, it's going well. We had some serious bouts of wind, but other than that, things are fairly well set up here. We've got some continuous time lapse going.
It's starting, Adam. I think. Adam, it's starting.
Oh wait, Jim, this is the big piece is starting to calve. Let me call you back.
Call him back.
Okay, bye.
Still going? Yeah. In that V section right there. Holy shit, look at that big bird rolling. All four running, right?
Yeah. Look at that. You see how, look at the whole thing.
The calving face is 300, sometimes 400 feet tall. Pieces of ice were shooting up out of the ocean 600 feet and then falling. The only way that you can really try to put it into scale with human reference is if you imagine Manhattan. And all of a sudden, all of those buildings just start to rumble and quake and peel off and just fall over and roll around. This whole massive city just breaking apart in front of your eyes. We're just observers, these two little dots on the side of the mountain. And we watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
Okay, so just a quick recap of the two videos that I just showed. The first video was a calving event on Holgate Glacier in Alaska, which as you may have learned earlier in this presentation, glaciers in Alaska are all alpine glaciers, so that's kind of like what a stereotypical alpine calving event looks like. And the second video was a video of the largest recorded calving event ever, to my knowledge, still to this date, and that calving event occurred off of Greenland, so that was an ice sheet calving event. Which, you know, is a much larger event, and you certainly wouldn't have wanted to be on the cruise ship that they were on in Alaska near the terminus of that Greenland ice sheet when that calving event occurred, because it would have been much more destructive. So let's talk some more about the mass balance or the budget of a glacier. So the glacial budget is the balance or lack of balance between accumulation and loss of ice. As was sort of explained in the video regarding that ice shelf in Glaciation that was that had the massive calving event. A change in the balance between accumulation and loss of ice can cause very fast melting of glacial ice or accumulation of glacial ice. So the loss of ice at the lower end of the glacier is called ablation, so that encompasses calving events as well as just melting at the lower end of the glacier. And if accumulation exceeds loss, then the glacial front advances. So the glacier grows and continues to expand downslope. However, if ablation increases and or accumulation decreases, then the ice front or the end of the glacier will retreat. And this can be calculated with a simple equation of inflow minus outflow equals change in storage. So if your outflow of glacial ice in the form of melting or sublimation or calving, etc., is greater than the accumulation of ice, then your change in storage will decrease and your glacier will start to shrink. Alright, so we've talked about how glaciers move and grow and shrink. But at the beginning of the lecture, I talked about how glaciers are involved in both the hydrologic cycle and the rock cycle. So let's talk about how they're involved in the rock cycle. Well, it's because they're capable of great erosion and sediment transport. And glaciers erode the land primarily in one of two ways. The first way is called plucking. So as a glacier flows over bedrock, it loosens and lifts blocks of rock in a process called plucking. So earlier in this lecture, when I showed you geologic evidence of a drop stone, that massive piece of rock was likely plucked from bedrock as the glacier grinded over top of the bedrock. The second way that glaciers erode is through abrasion. So rocks that are being carried within a glacier act like sort of a sandpaper and smooth and polish the rock surface that the glacier and the sediment on the bottom of the glacier is grinding over top of. And that process is called abrasion. So a drop stone was a good example of evidence of glacial plucking. But another thing that's a good example that is on land is a glacial erratic. So if you've ever been kind of driving around or living in an area where there's wide open farmland and you can see forever, and then there are randomly massive rocks sticking up above the surface of the earth that are not connected to the bedrock, those are most likely glacial erratics, because there is pretty much no other geologic mechanism that is powerful enough to move rocks this big. So again, these are rocks that were plucked from the bedrock as the glacier moved over the Earth's surface. Now on to glacial abrasion. Glacial abrasion produces both rock flowers, which is basically just pulverized rock. So if you have this insanely heavy glacier with a bunch of sediment on the bottom of it, some of which might be quartz, finely ground quartz, then it just pulverizes the rock that it's grinding over in some situations, or in a lot of situations, and produces what's known as rock flour. And in a lot of places where you have some sort of inlet or something that a glacier is flowing into, could be an alpine glacier in this case, you might notice that the water is quite green, and that's because the water often contains a bunch of rock flour. A second thing that glacial abrasion produces are striations, and these are grooves in the bedrock. And so a lot of times you can see sort of parallel lines or grooves in the bedrock where a glacier and the sediment on the bottom of the glacier ground over that bedrock when a glacier existed there. And interestingly enough, you can go to Central Park in New York City, and the glacial erratics that you see sticking up from the ground in the park have glacial striations on them because the last glacial maximum extended the ice sheets in North America to down below Central Park in New York City. So glacial erosion, whether by plucking or abrasion, is controlled by the rate of movement of the glacier, the thickness of the ice. So the thicker the ice, the greater the weight of the ice, the greater the pressure on the underlying rock. The types of rock fragments trapped in the ice. So if you have very soft rocks trapped in the ice, and that ice is grinding over a bedrock, that's not going to produce as much rock flour as if you have very solid rock fragments trapped in the ice, like rocks with a lot of quartz, for example. And then the erodibility of the surface below the glacier. So again, if you have extremely soft rock below a moving glacier, then the rock fragments are more likely to cause additional abrasion, versus if you have very solid rock below the glacier, then the rock fragments trapped in the ice are less likely to cause very significant abrasion and erosion. So these photos in this slide show some really good examples of glacial abrasion in the form of striations on the left. So you can see you have this bedrock, and you have scratches and grooves in the bedrock that run parallel to one another in that photo. And then on the right, you can see in Yosemite National Park that a glacier polished the granite and just ground it to an extremely smooth surface in this case. And you might find some striations here as well. So I sort of mentioned this earlier in the lecture, but it's important to note when you're analyzing landforms and you see evidence of previous glacial activity, that landforms created by valley or alpine glaciers and ice sheets are very different. So alpine glaciers create sharp and angular topography, versus ice sheets subdue most topography. And I think the reason for this is quite clear, because alpine or valley glaciers carve out valleys in a U shape, and ice sheets grind the top of mountains and make them less sharp or angular, because ice sheets are so massively thick that they don't only flow in valleys, they also flow over top of mountains. So let's talk about what valleys created by glacial erosion look like. So glaciers widen and deepen valleys, creating a U-shaped glacial trough, as opposed to a V-shaped valley that is what's formed by a stream that continues to downcut in the center of the valley. Ice doesn't necessarily conform to the valley the same way because it's a solid, so it creates more of a U-shaped glacial trough. Glaciers also tend to straighten valleys, removing sharp curves and creating truncated spurs or triangular shaped cliffs. So glaciers in a main valley, or also known as a trunk valley, typically erode more sediment than tributary glaciers. Tributary glaciers being glaciers coming from smaller valleys that flow into the main or trunk valley. The tributary glaciers, as a result, typically create hanging valleys. So the reason that they create hanging valleys is because they don't erode as deep as the glacier in the main or trunk valley, because the glaciers are smaller and have less energy and power to grind away the valley and erode it deeper into the earth. Okay, so we've talked about how glaciers erode away material by plucking and by abrasion. But now we're going to talk about some of the erosional features that are formed by alpine glaciers, or evidence of this type of erosion. And so before I get into all these different types of glacial features, I want you to just take a moment to think about how you think the following glacial features were formed. So in this figure that I presented here, you can see a picture of an arête, a horn, a medial moraine, and a hanging valley. And I'll give you a minute to think about how these features might be formed, and then I'll go through all of these glacial features one by one and explain to you how erosion forms these features. Okay, so make sure to focus on where the glaciers are and therefore how they may be eroding the mountainous environment in which they formed. Okay, so the first glacial feature that I want to talk about is a U-shaped glacial trough. I mentioned earlier in the lecture that glaciers typically carve out U-shaped valleys, which look significantly different from the V-shaped valleys that are typically carved out by flowing water. And again, this is because if you have liquid water, then it will continue to, as a river flows down valley, downcut into the center of the valley, versus a glacier is made of ice, which isn't going to just channel into the most incised point in the valley because it's a solid. So in fact, it sort of carves out the sides of the valley a lot more than flowing water would. And that's why you end up with these U-shaped glacial troughs. So really, anytime you see a valley that's shaped this much like a U, it was probably formed by a glacier moving through the valley and plucking up bedrock and abrading away bedrock and sediment as well. So another glacial feature that's formed by erosion is a medial moraine, and we happened to already talk about this a couple times, but this is an actual photograph of an alpine glacier and another alpine glacier that intersects the larger alpine glacier, and then you can see the medial moraine that is formed in the middle of the glacier that continues downslope from where those two glaciers meet. And as I mentioned before, this is evidence of sediment getting ground up by both glaciers, kind of coming to a head and getting deposited in between the two glaciers, even though they're now connected into one larger glacier that's continuing to move downslope. So glaciated valleys also contain a couple more glacial features to be aware of. So one is called a cirque, and this is a bowl-shaped depression typically found at the head of a glacial valley. So if you're ever looking at a mountain and you see a bowl-shaped depression near the mountaintop, especially if you're in Idaho or anything further north, or if you're looking at really high mountains like in the Rockies, there's a fair probability that that's actually a cirque that was once carved out by a glacier. And when two glaciers exist on opposite sides of a mountain, and both of them have cirques at the head of the glacial valley, then the dividing ridge between those two cirques is eroded away by the cirque, creating a gap called a col. Glaciated valleys are also often filled lower down in the valleys with paternoster lakes, and these lakes form after parts of the bedrock are lifted and plucked by the glacier, and then those depressions within the glaciated valley, fill with water. So this is a really good example of what paternoster lakes might look like. So you can see here that you're looking at a U-shaped valley. It's very textbook U-shaped valley carved by a glacier. And then you can see the series of paternoster lakes filling out the valley as large hunks of bedrock were plucked by the glacier moving down valley, and then those depressions got filled with water that is typically melting of the snow or glacier further up valley. And this is a really good textbook photograph of a cirque. You can see how the head of the glacial valley really carves out that bowl shape into the side of the mountain. Glaciated valleys are also often filled by fjords, which are deep, steep-sided inlets. Typically, this is referring to an ocean inlet. And these are basically drowned U-shaped glacial troughs that form when sea level rises relative to the land that was originally carved out by the glacier. And these aerial photographs of Western Norway show really good examples of fjords. And then the photograph on the bottom here shows you a more close-up view of what one of these fjords might look like. So another landform commonly created by glacial erosion is something known as an arête. And an arête is basically just a sharp-edged ridge formed by parallel U-shaped valleys. So if you have a glacier moving down one valley and then another glacier moving down another valley adjacent to that valley, then the glacier will be carving out two U-shaped valleys, and what's left in between is a sharp-edged ridge. And so this photograph here is a pretty good example of what an arête looks like, where you can see this hiker hiking along an arête, and you can see sharp drop-offs on both sides carved by the U-shaped valleys from glaciers on either side of the arête. So a horn is another landform created by glacial erosion, and it is basically a pyramid-like peak that results from the erosion within 3 or more cirques. So if you have 3 or more glaciers, and the head of those 3 or more glacial valleys are being carved out by cirques, then ultimately you're left with a pyramid-like peak. And the Matterhorn, displayed here, aptly named, I suppose, is a really good example of a horn. And then lastly, another landform caused by glacial erosion is roches montagnes. which is an asymmetrical knob of bedrock produced by continued glacial erosion. And in this case, glacial abrasion smooths the gentle slope facing the oncoming glacier, and plucking steepens the opposite side of the slope as the ice sheet rides over it. And this is what a roches mountainous looks like. And you can picture the ice flowing from right to left in this case, where you have glacial abrasion on the right and then plucking on the left as the ice flows down over this bedrock. Okay, so landforms don't only form by glacial erosion, but they also form from glacial deposition. So as glaciers melt, the rocks and sediments in the glaciers are typically deposited because the glacier is no longer carrying them. So in terms of glacial deposits, glacial drift is a term that refers to all sediments of glacial origin. And there are two primary types of glacial drift, or glacial sediments. One is known as till, and till is a material that is deposited directly by the ice. And then a second is called stratified drift, and this is when sediments are laid down by glacial meltwater. So the difference is that till is deposited directly by the ice, and stratified drift is deposited directly by meltwater. So this photograph shows a good example of glacial till deposits. And you have an unsorted mixture of many sizes of sediment, and not many other geologic forcings would leave such an incredibly unsorted pile of sediment as a glacier in the form of glacial till. And then if you were to closely examine some of the rocks in the glacial till, you can see that some of those rocks have been scratched as they were dragged along by the ice, and were, some of the particles that caused abrasion when the glacier was moving across the Earth's surface. So now that everyone hopefully understands what till is, which is sediment that's directly deposited by the ice of a glacier, you might note that there are multiple types of landforms that are actually made of till. So one of those types of landforms is a lateral moraine, which is an accumulation of debris on the side of the glacier as it moves down valley. And another one of these types of landforms is a medial moraine. And you might note that we discussed medial moraines earlier in the lecture, and you saw that when you had two alpine glaciers converge upon one another, it formed a medial moraine. And the sediment that comprises that medial moraine is from the lateral moraines of both of the alpine glaciers that converged upon one another. And it just so happens that then the medial moraine will be somewhere within the larger glacier that's created by the convergence of the two smaller glaciers from higher up in the mountains. So this photo here shows a really good example of the formation of a medial moraine. You can see that you have one glacial valley on the right, and then you have another glacial valley on the left, and where they converge, the lateral moraines from both of those glacial valleys form a medial moraine. And in fact, in this specific glacier, you can see that you have several glacial valleys that converge and form several medial moraines. It's pretty cool, actually. And then finally, another type of landform made of till are end or ground moraines. So before I talk about the definitions of those two different types of moraines, you need to think of a glacier as moving sediment in a similar way to how a conveyor belt might move a product. So regardless of the movement of the glacier, sediments are constantly moved forward and then dropped at the terminus or the end of the glacier. So an end moraine is an accumulation of debris that forms at the terminus or the end of the glacier as a result of that conveyor belt moving sediment. And then a ground moraine is sort of a rock-strewn plain created as the glacier retreats. So you can think of the end moraine as, the terminus of the glacier at its maximum extent, and then a ground moraine is created during the glacial melt period. So you can think of this as during the spring or summer as the glacier is retreating. And each step along the way as it's retreating forms another ground moraine because that conveyor belt is continuing to work regardless of whether the glacier is growing or shrinking at the time. So here you can see an example of an end moraine when the accumulation of the glacier equals the ablation of the glacier. And so the terminus of the glacier is stationary, and that ultimately results in an end moraine. Okay, so one more landform made of till are drumlins. And these are sort of smooth, elongated, parallel hills that are composed of till. And they're formed by ice sheets, so they don't form in alpine glacier environments. And the steeper side of the drumlin faces the direction that the ice advanced, and the shallower side of the drumlin faces the side the ice was coming from. And there's still some speculation on exactly how drumlins are formed, so this is like a pretty active area of research in glacial geology if anyone is interested in reading some more about drumlins and kind of going down that rabbit hole. So there are other glacial landforms that are created or made of stratified drift rather than till. And some good examples of these are outwash plains and valley trains. So glacial meltwater, to backtrack for a second, you need to recall that stratified drift is created by glacial meltwater rather than the glacier itself. So glacial meltwater that's choked with sediment flows onto a flat surface and then drops its sediment load and builds a broad ramp-like surface. And that creates braided streams. So if you recall, that's why braided streams are created so frequently from glaciers. And so basically, from this glacial meltwater, you can get outwash plains, which are associated with ice sheets, or valley trains, which are associated with mountain valleys. And both outwash plains and valley trains are made of stratified drift. So a couple other types of landforms that are made of stratified drift are ice contact deposits, which are stratified drifts that remain once the ice melts away. So in this case, you have meltwater that flows over within and at the base of motionless ice deposits. And then a kame is more of a steep-sided mound, and kame terraces occur when glacial ice occupies a valley and streams flow alongside that ice. And then you can have kame deltas, which form on top of the ice. So here's a good example of an ice contact deposit or stratified drifts that remain once the ice melts away. So this is from my home state, actually, and this particular type of ice contact deposit is called an esker, which is a narrow, sort of sinuous or windy ridge and it results from subglacial stream flow. Now you might be asking yourself, why would stream flow ever create a ridge rather than a valley? Because streams typically erode away sediment. And while that's true in a subglacial environment, a lot of times there's nowhere for the sediment to go because only a narrow path is being carved out by water in the subglacial environment, so there's no sort of floodplain, so to speak. And so all of that sediment ends up getting deposited where the stream was flowing, and thereby creating an esker. So this slide shows a retreating glacier and then all of the sort of common depositional landforms that we've talked about that might be formed before or during a glacial retreat. So you can see the esker, which was again a subglacial stream flow that flowed through a tunnel beneath the glacier. You can see a braided river, which is kind of the type of river that forms at the outlets of glaciers. And you can see a drumlin field, and then a kettle lake and a kame as well. So we haven't really talked about kettle lakes yet, even though you can see from the previous slide that they are also a common landform. So kettles are the result of blocks of ice calving from the front of a receding glacier and becoming buried by glacial outwash. So if you have a glacier receding and a big chunk of ice calves off of the glacier and then gets buried by glacial outwash, so a bunch of sediment piles on top of that giant chunk of ice, then ultimately when the ice melts, you're left with a depression, and that depression is often filled with water because you have a glacier that just melted, and that's the reason that the depression was formed in the first place. And so it leaves these kettle lakes behind. So there are some other major effects of Ice Age glaciers outside of just the formation of erosional and depositional features. So one of them that's quite interesting is crustal subsidence and rebound. So ice sheets are so massive and so heavy that they literally cause a downwarping of the Earth's crust itself. They cause it to sink into the asthenosphere, so to speak. However, after the glacial melts, the crust gradually rebounds. So if you think about the implications of this, especially in coastal areas, you may have areas where, during the Ice Age, when the ice sheet existed in that location, the crust was actually below sea level. And then after the ice receded and the crust began to rebound, then the crust was higher than sea level. And not just because of changes of the amount of water in the oceans, but also because of the actual elevation of the crust itself changing as it's no longer burdened with the immense weight of the ice. And speaking of sea level changes are another effect of Ice Age glaciers. So, for example, during the last glacial maximum, or the last maximum extent of the ice sheets in the last Ice Age, sea level was about 100 meters lower than present level because there was that much more water trapped in ice on Earth than there is today. And another example that's very relevant today in terms of sea level changes is portions of the Antarctic ice sheet have been melting and may continue to melt more if global temperature continues to rise, and specifically the temperature in the Antarctic region continues to rise. And if the entire Antarctic ice sheet melted, then sea level would rise by 60 or 70 meters. So imagine the world today, and then imagine if the elevation of the oceans was another 200 feet higher, how different the continents would look, and how many places that people live today would simply be submerged. Hopefully that doesn't happen, obviously, but just sort of something to note when folks talk about global climate change and sea level rise, how massive an impact just the Antarctic ice sheet melting would have. So speaking of both changes to sea level as a result of glaciation and the last glacial maximum, this figure shows a really good example of the maximum extent of glaciation during the last ice age, which was about 18,000 years ago. I mentioned earlier that the last ice age ended, 10 to 12,000 years ago, but the maximum extent of the glaciation ended about 18,000 years ago. And you can see what the coastline of the United States would have looked like during the last glacial maximum 18,000 years ago, because 100 meters or 330 feet of because sea level was 100 meters or 330 feet lower than it is today. So the entire continental shelf, basically, of North America was part of the landmass back then and is now submerged as a result of the melting of glacial ice. All right, that's all I have for you this week. Thanks so much for listening, and please be sure to read chapter 15.5 and beyond so you can learn about glacial lakes, specifically, for example, Lake Missoula, which is pretty close to home here, and some other types of landforms that I didn't get to cover in this lecture, as well as some of the previous ice ages. So mostly this time around, we just talked about the ice age that ended 10 to 12,000 years ago and had its last glacial maximum 18,000 years ago. But I didn't get a chance to cover many of the ice ages that occurred before the last ice age. So please be sure to read about that. And I'll be having office hours again this week on Wednesday from 5:30 to 6:30. So please chime in on Zoom if you have any questions at all about this material or about the exam. Thanks, and talk to you soon.